Temporal logic is a branch of logic that provides formal tools for reasoning about time and temporal relationships. While classical logic is timeless and evaluates sentences simply as true or false, temporal logic allows us to express how truth values change over time. It enables us to reason about what has been the case, what is currently the case, and what will be the case. Because of this, temporal logic plays an important role in philosophy, linguistics, computer science, artificial intelligence, the formal analysis of dynamic systems, and other fields. Temporal logic is especially useful for analyzing statements involving change, persistence, processes, and events. For example, we may want to formalize claims such as "it will always be the case that," "it will sometime in the future be the case that," or "it has always been true that." Classical logic cannot adequately capture such temporal distinctions, since it treats all truths as fixed and unchanging, at least not in a natural way. Temporal logic introduces operators that can be used to talk about what has been the case, what will be the case, etc. Common temporal operators include f, at some future time it will be the case that; g, at all future times it will be the case that; p, at some past time it was the case that; and h, at all past times it was the case that. In linear time temporal logic, these operators are sometimes read as eventually, always, once, and historically. Using these operators, we can express temporally rich claims. For instance, GA means that A will always be true in the future, while FA means that A will be true at some future time. Temporal operators allow us to distinguish between temporary and permanent truths, and to formalize notions such as persistence, recurrence, and inevitability. The syntax of propositional temporal logic extends classical propositional logic by adding temporal operators. Starting from propositional variables and classical connectives such as negation, conjunction, and disjunction, we introduce temporal operators like f, g, p, and h. If A is a well-formed formula, then FA, GA, PA, and HA are also well-formed formulas. Temporal formulas can be nested, allowing expressions such as GFA. It will always in the future eventually be the case that A, or P not GA, at some time in the past, it was not always going to be the case that A. As with modal logic, the syntax alone does not determine meaning. This is provided by the semantics. The most common semantics for temporal logic is based on time structures rather than possible worlds. A temporal model typically consists of a set of time points, a temporal ordering relation, such as earlier than or later than, a valuation function assigning truth values to propositional variables at each time point. Temporal operators are interpreted relative to this structure. For example, GA is true at a time t if and only if A is true at all times later than t. FA is true at t if and only if A is true at some time later than t. Different assumptions about the structure of time, such as whether time is linear or branching, finite or infinite, lead to different temporal logics. Different temporal systems correspond to different conceptions of time. Is there a first moment in time? Is there a last moment in time? Is time discrete or infinitely divisible? Is time linear or circular, branching or non-branching? Linear temporal logic assumes that time is linear. At each moment, there is exactly one possible future. This is often used in computer science to reason about programs and processes. Branching time logics, such as computation tree logic, allow multiple possible futures, reflecting indeterminism or choice. Some systems include only future operators, while others include both past and future operators. Adding past operators often increases expressive power, but may also affect computational complexity. Each system captures different intuitions about how time works. Several proof methods are used in temporal logic. Hilbert-style systems extend classical axioms with temporal axioms and inference rules. Natural deduction systems introduce rules for temporal operators, often using indexed formulas or assumptions about time points. Semantic tableaux are widely used. They attempt to build countermodels by systematically decomposing temporal formulas over time structures. In computer science, automata-based methods are especially important. Temporal formulas can be translated into automata that recognize sequences of states satisfying the formulas. This approach underlies many applications of temporal logic in verification. Propositional temporal logic deals only with propositional variables and temporal operators. Quantified temporal logic combines temporal logic with predicate logic, allowing quantification over individuals whose properties may change over time. This raises philosophical and technical questions about identity across time, persistence, and existence. For example, should quantifiers range over the same individuals at all times, or can the domain vary over time? Different answers lead to different semantic frameworks and metalogical properties. In temporal logic, a sentence is logically true if and only if it is true at every time point in every model. A sentence is logically false if and only if it is false at every time point in every model. A sentence is logically contingent if and only if it is true at some time point in some model and false at some time point in some model. These notions generalize classical logical concepts, but they depend crucially on the temporal structure of models and the interpretation of temporal operators. A formula B is a logical consequence of a set of formulas S if and only if in every temporal model and at every relevant time point B is true whenever all formulas in S are true. An argument is valid if and only if its conclusion is a logical consequence of its premises. As in classical logic, validity concerns form rather than content, but temporal structure plays a crucial role. Many propositional temporal logics are sound and complete with respect to their intended semantics. Some are decidable, though often with high computational complexity. Quantified temporal logics typically lose decidability and sometimes completeness, much like predicate logic. Temporal logic extends classical logic by providing formal tools for reasoning about time, change, and persistence. Through its syntax, semantics, and proof methods, it offers a powerful framework for analyzing temporal reasoning in philosophy and formal sciences. Despite its technical challenges, temporal logic remains an important tool for understanding dynamic aspects of reality.